Lesson 3-2 gets into all about what a function actually is. So first let's go over some terminology, specifically function. We'll start off with. Last lesson we talked about relations and how a relation is a set of ordered pairs. So it's all of our x, y values put together. Well, a function is a kind of relation. It's a relation in which there's only one value of the dependent variable for each value of the independent variable. Now that might sound confusing, putting our dependent variables and independent variables together. Basically, a way to say it is each x value has only one y value. So if you had a big set of numbers or a big set of ordered pairs, that relation, if in that relation each x value only gave you one y value, it would be a function. Now here's an example of what I mean by that. These relations, or these sets of ordered pairs are given as tables. So in this set, we have our x and our y values. Remember, x is our domain, y is our range. Our x values, we've got 0, 2, 3, and -6. Our y, we have 1, 7, -4, and 10. So we have the points 0, 1, 2, 7, 3, -4, and -6, 10. Now notice in this set of 4 points, x is not repeated at all. We just have 0, 2, 3, and -6. We never repeat. So this one is, in fact, a function. If we look over at this example, we have, again, domain x, range y. We have the points 0, 6, 1, 3, 0, 8, 2, 5. If you'll notice, though, 0 happens twice. Okay, we have two x values giving us different y values. We have a 6 and an 8. So this one is not a function because x happens twice, giving us different y values. So that's what we mean by a function. Again, it's just a kind of relation. The vertical line test is a method of determining whether a relation is, in fact, a function. So it is a function. This is how the vertical line test works. It is a function if no vertical line intersects the graph at more than one point. Now, one thing to know is this only works when you're looking at a graph. Okay, so if you're not looking at a graph, if you're just looking at all the points, you can't necessarily use the vertical line test. Okay, only if you have a graph and you're looking at it and you can draw vertical lines on there, that's when you can use the vertical line test. And we'll do that. We will show you what it looks like to use a vertical line test. One more piece of terminology. Function notation. This is a way to name a function that is described by an equation. So if we have the equation y equals 3x minus 2, we can simply write it as f of x equals 3x minus 2. This little piece here, f of x, it means the same thing as y. Okay, it's like just kind of replacing y with this function of x. Now, another thing, we read this little piece here, f parentheses x, close your parentheses, we read it as f of x. So if I were to plug in something for x here and say 1, we would read it off as f of 1. And what this means is we're plugging in 1 for x. So if right here I had f of 1 equals, well, I would have 3 instead of times x would be 3 times 1 and then minus 2. That's what each of these pieces mean. So let's look at ways to represent a function. Now we can have a table, we can have an equation, or we can have a graph. Okay, if we look at a table is simply just examples of the points. Now sometimes a table is going to have everything, so just like when we had relations that were only a few points on a graph, that table could completely show you everything. But sometimes the table won't show absolutely everything. So remember, this table, our x values are our domain, our y values are our range, and it's important to remember this table has only some of the points of the function. All three of these, the table, the equation and the graph are trying to show the same exact function. Now remember, because x is our domain and y is our range value, but we have this function notation f of x, we can actually call our range right here in the table, we can say x and f of x. And we can either call it x and y, or we can call it x and f of x. Okay, now looking at our equation, oops, this isn't examples of points, this should be a general rule. Okay, we should be able to look at this, our equation, and say this will cover every single point we're looking for. Notice on our table we don't have any like decimals or fractions or anything like that. If I wanted to, I could plug in decimals or fractions into this rule, into this equation. So this might be a little more kind of a general statement to say any of our x values that you want to be able to plug in, f of x in the end, that's what will come out of it. That will be your range value. This is more just a way to say it generally. This is an example of just some points. A graph then is a visualization or a picture of what it's supposed to look like. If I were to plug in these points over here, like -1, 3, that would be right here. 0, 0 would be right here. 1, -1 would be right here. 2, 0, 3, 3. So you can see how all these points then, it's like we have a huge table with a ton of points in there, and that's why we hit all these little points in here, all of these decimal values and fractions, and we plotted them all together so closely that they made a line. So this is actually like an infinite amount of points all right next to each other, make up that graph. So let's get into some examples of how this all looks, or what it looks like to be a function or check for a function. When we're using these graphs, always use the vertical line test. That'll be the easiest way to check it. So I have a vertical line right here, this blue piece. I'm just going to slide it across here and see if it hits more than 1 point on my red graph. I think yours still black on your paper, but mine will be red on here. Now notice, here's an equation, the general rule for my function, x equals 1/3 y squared minus 2y plus 5. Here's a graph to represent what that equation looks like. Now I grab my vertical line. As I slide across the side here, I'm not touching any points yet until right here I've touched 1 point. Okay, it's like the corner of it, or the vertex of this graph. Okay, so right now I'm only touching 1, but as I slowly slide this way, maybe we'll stop like right here or so. Notice how I'm touching 2 different points here. Right here and right here. So I have a vertical line that's touching more than 1 point. And again, I could move my vertical line over here and I'd still be touching more than 1 point too. But as long as I can draw a vertical line at any spot that happens to be touching more than 1 point, like 2 points on top of each other, we would say no, that one is not going to be a function. It does not pass this vertical line test. Okay, so let's look at example B. In this case, my rule or my equation is y equals -x cubed plus 4x squared minus 6. So that kind of makes this swirly looking graph. It kind of starts at the top, comes down, turns around right here, comes back up. Kind of like how this one had that U shape. Well, we have a U shape, but then it turns around and does another U shape. Well, if that's the graph or the visualization of our equation there, our general rule, let's again slide our vertical line. Now right here, it's touching 1 point, and it kind of looks like we might be touching a lot, but that's because we have a pretty thick line. Technically, each of these spots is only touching 1 point. My vertical line is never touching more than 1 point. So we come up here, again, it's still only touching 1 all the way through. And these, because of the arrows, it's going to continue on forever like that. But again, if I were to continue to slide this across our graph, it would still only be touching 1 point at any time. So because it's always touching just 1 point, we would say, yes, this one is going to be a function. it does pass the vertical line test. Let's look at letter C then. In this one, we don't have a graph. We just have a set of points, 1, -4, 2, -4, and 6, -4. For these ones, we'll always check the domain. So if you just have a set of points or like a table, like over here, you always just check the domain. Now, if we look at our domain, it's all the x values, so 1, 2, and 6. And notice that it never repeats itself. If we look up here, this spot, our x was 5, well, it repeated itself. We had a 5, 0, and we had a 5, 6. So x repeated itself in this case. In this relation, x never repeats itself. Just 1, 2, and 6. So because the x never repeats, we would say yes, this one is in fact a function. So let's do the same thing. We're going to check our domain. In this case, so we have domain and range. We have -2, 0, 5, and 5 for our domain. Now one thing to be careful of here, notice we have 5 and 5 happening twice. This time 5 gives us a 9. This time 5 gives us a 6. So if we were going to try to graph this out, if we put a little graph here, I went out 5, well, one of my 5s would go up to 6, one of my 5s would go out to 9. These would be my 2 points. If I were to do the vertical line test then, grab my vertical line, slide it here, oh, it would touch both of those points at the same time, 5, 9 and 5, 6. So it would not pass a vertical line test. So we would say no. This one does not, or is not a function because 5 happens twice. Let's look at some examples of evaluating a function. Now evaluating basically just means you're plugging in that value. So normally we might say y equals something, and then we'd say we want to know y when x equals this. Well, now we can just say evaluate at, in this case, f of 2. So if f of x equals 3x minus 4, f of 2 means we're just plugging in 2 everywhere we see x. So f of 2 equals 3 instead of times x, it's times 2, and then minus 4. Well, 3 times 2 is 6, so f of 2 means 6 minus 4. We can simplify that further. 6 minus 4 is 2. So f of 2 equals 2. That, we would say, is our solution. F of 2 equals 2. So let's look at letter B in this case. G of x equals x squared plus 2x. And we want to find g of 5. Well, again, that just means we're plugging in 5 everywhere we used to see x. So instead of x squared, it's now 5 squared. Instead of 2 times x, it's now 2 times 5. So then we can simplify. 5 squared is 25. 2 times 5 is 10. So g of 5 is 35. Again, we just circle that. That is our solution. That's our answer. Last one then. H of t. Now in this case we don't have x. We're not using x. Our variable that we're using is t. So h of t equals, so these bars mean absolute value. So the absolute value of t plus 2.1. And we want to find h of negative 8.9. Well, like before, we're simply just plugging 8 or negative 8.9 in for t. So h of negative 8.9 equals absolute value of negative 8.9 plus 2.1. Simplifying that down, negative 8.9 plus 2.1 would be negative 6.8. So we have the absolute value of 6.8 would be just simply 6.8. So again, this is our end solution. That would be how you evaluate these ones. So these last couple ones, they're a little bit extra steps in evaluating. If we look at this one, letter A from example 3, we have g of 3 minus 1. Well, since the minus 1 part is outside of the parentheses, we have to do that part last. So first we find out what g of 3 is, then we'll minus 1 from that value. So g of 3 means instead of x cubed, it's 3 cubed. Instead of minus x, it's minus 3. 3 cubed is 3 times 3 times 3, which is 27. So 27 minus 3 means that g of 3 equals 24. 27 minus 23 is 24. So g of 3 minus 1 means we're doing 24 in this spot, this g of 3, then minus 1. Which means that, get rid of this, g of 3 minus 1 equals 23. This is how we would write our solution. Letter B. S of t equals 7t plus 6. And we want to find S of A. Now this means we're plugging in A everywhere for t. Now they've kind of introduced a new variable, A, and they never told us what A equals. So when we plug it in, S of A equals 7A plus 6, or 7 times this value A. Well, we don't know what 7 times A is because they never told us how big A is. So all we can do is just call it S of A equals 7A plus 6. Okay, it didn't really do anything to this equation here. Instead of S of t, it's now just S of A. So instead of 7 times t plus 6, it's 7 times A and then plus 6. That's all we can change on that one. In this equation, or this function, we have f of n equals 4n. And we want to find f of 2c minus 3. Now again, this means we're plugging in 2c minus 3 for n. So everywhere we see an n value, we replace it with 2c minus 3. So f of 2c minus 3 equals 4 times this amount, 2c minus 3. Well, that means we have to use our distributive property. We have to do 4 times 2c. That would give us 8c. Then we have to do 4 times minus 3, or like a negative 3. That would become minus 12. And again, 8c minus 12, we can't simplify it any further because they haven't told us what c equals. So again, this is our final answer. We're just plugging this piece here in for n and simplifying it as much as we can.